Hi everyone, in this recording we'll be going over nonlinear inequalities. By the end of this presentation, our goal is that you'll be able to solve polynomial inequalities, you'll be able to solve rational inequalities, you can use the test intervals and key numbers, and you'll be able to model and solve real-life nonlinear inequality problems. A polynomial can change sign only at its real zeros, so those are values that make the polynomial equal to 0. So these zeros divide the number line into open intervals called test intervals, on each of which the polynomial has a constant sign, either positive or negative. So the test intervals for a polynomial inequality. So first, in order to construct these test intervals, we find all real zeros of the polynomial and arrange them in increasing order. These zeros are the key numbers of the inequality. Then we determine the test intervals using the key numbers. So from negative infinity to x1, our first zero, then x1 to x2, our second zero, and then our last zero to positive infinity. So then we test one representative x value in each test interval and evaluate the polynomial. The sign of the result tells you whether the polynomial is positive or negative on that interval. So for example, we are told, solve x squared minus 2x minus 3 less than 0. So first we factor the polynomial. X squared minus 2x minus 3 is equal to x plus 1 times x minus 3. So setting each of those portions equal to 0, x plus 1 equal to 0 will imply that x is equal to negative 1, and x minus 3 equal to 0 will imply that x is equal to positive 3. So now these three zeros divide the real line into three test intervals, from negative infinity to negative 1, from negative 1 to 3, and from 3 to positive infinity. Now we can choose some representative x values between those intervals. So from negative infinity to negative 1, we can choose the value negative 3. From negative 1 to 3, we can choose the value 1. And from 3 to positive infinity, we can choose the value 4. Plugging in each of those values and the resulting y will tell us the sign of the polynomial within that interval. So when the inequality is less than or greater than, the solution set does not include the endpoints, the zeros. If the inequality is less than or equal to, or greater than or equal to, the endpoints are included. So now we have some examples. 4x squared minus 5x is greater than 6. So first we rewrite in standard form. So 4x squared minus 5x minus 6 is greater than 0. So we want to find for what values will the function be greater than 0. So first we factor. 4x squared minus 5x minus 6 in factored form is x minus 2 times 4x plus 3. So we set each of those portions equal to 0. So x minus 2 equal to 0 will imply that x is equal to positive 2, and 4x plus 3 equal to 0 will imply that x is equal to negative 3 over 4. So now we order them from in increasing order. So our smallest zero was x is equal to negative 3 over 4, and our greatest one is x is equal to 2. So now we can construct our test intervals. So we have negative infinity to negative 3 over 4, negative 3 over 4 to 2, and 2 to positive infinity. Now we can choose representative x values within those intervals. So for our first one, we chose negative 1. So f of negative 1 will equal positive 3. So our function will be positive on that interval, so that holds. So our function is greater than 0 on that interval, so that interval will be part of our solution. For f of 0, we got negative 6, so that portion will not hold for our inequality. For the interval 2 to infinity, we chose the value x is equal to 3, so f of 3 is equal to 15, which is positive. So our function is positive on that interval, so that interval will also be part of our solution. So our solution is negative infinity to negative 3 over 4 union 2 to infinity. Those are the intervals for which the function 4x squared minus 5x minus 6 is greater than 0. Now we are given another example. Solve 2x cubed minus 3x squared minus 32x minus 48. So first we write in standard form, meaning we move the negative 48 to the left-hand side, so that we'll have the function on the left-hand side greater than 0. Now we can factor the function, so 2x cubed minus 3x squared minus 32x plus 48 is equal to x minus 4 times x plus 4 times 2x minus 3. So after setting each of those portions equal to 0 and ordering our zeros from least to greatest, we see that x is equal to negative 4, x is equal to 3 over 2, and x is equal to 4. So now we can construct our test intervals, choose our representative x values within those intervals, and test them to see what the sign of the function will be. So for the interval negative 4 to 3 over 2, we got positive. So that means that the condition holds on that interval, so that'll be part of our solution. And for the interval 4, infinity, the function is also positive. So that means that the condition holds, and that will be part of our solution. So our final solution is negative 4 to 3 over 2 union 4 to infinity. So now one of the applications is profit from a product. So profit is equal to revenue minus cost, or P is equal to R minus E. So we're given a question: what price can the company charge per calculator to obtain a profit of at least $190 million? So first, we set up our demand, revenue, and cost equations. So in our case, P will be equal to 100 minus 0.00001x, and x will lie between 0 and $10 million. So P in this case is the price per calculator, and x is the number of calculators sold. Now the revenue equation is given by x times P, so we'll do x times 100 minus 0.00001x. Now the cost equation is equal to 10x plus $2,500,000, where we are selling each calculator for $10, so $10 per calculator, plus a $2,500,000 development cost. So now we can plug in our revenue and our cost equations into our profit function, and that'll yield this quadratic: negative 0.00001x squared plus 90x minus $2,500,000. So now for the solution, we set up the inequality. So we want a price of greater than or equal to $190 million. So on the left-hand side, we'll put our inequality and greater than or equal to our price. So we will find the sales interval. So to do that, we solve the inequality, and that'll yield that x is greater than or equal to $3,500,000 and less than or equal to $5,500,000. So that means that this company must sell between 3.5 million and 5.5 million calculators. Now we find the price range. So we substitute the x values back into the demand equation. P is equal to 100 minus 0.00001x. So this will yield 45, or P is greater than or equal to 45 and less than or equal to $65. So that means prices between $45 and $65 per calculator will yield a profit of at least $190 million. So the profit is maximized near the vertex of the profit parabola. So here, any price between $45 and $65 yields a profit of at least $190 million. Now this is an example for graphing the solution set. So we are told to solve x squared minus x minus 6 less than 0 and to graph the solution set. So first we factor the polynomial x squared minus x minus 6. So that'll be x plus 2 times x minus 3. So then we set each of those portions equal to 0. So x plus 2 is equal to 0 will imply that x is equal to negative 2. And x minus 3 equal to 0 will imply that x is equal to 3. Now we will use those key numbers to create our intervals. So the smallest one was negative 2. So negative infinity to negative 2. Then negative 2 to positive 3. And then positive 3 to positive infinity. Now we choose a representative x value within each of those intervals. So for negative infinity to negative 2, we chose x is equal to negative 3. So plugging that into our quadratic, we got 6. So that is a positive value, and therefore the inequality does not hold on that interval because we are looking for less than 0. Now we have the interval negative 2, 3. So we chose x is equal to 0 for a representative value of that interval. And f of 0 will give us negative 6. So that is a negative number. Thus the inequality holds since we are looking for values less than 0. Now for the interval 3, infinity, we chose the value x is equal to 4. So f of 4 is equal to positive 6. So that value will not hold for this interval. So that means our solution set is the interval negative 2, 3. And because the inequality is less than, so strictly less than, the endpoints negative 2 and 3 are not included. So to the right, we just have the method over again. So first, you factor the polynomial if possible. 2, you determine the test intervals. 3, you test one representative x value in each interval. And then 4, you write the solution set based on the inequality that you are trying to check. So lastly, we have the graph check. So the graph of y is equal to x squared minus x minus 6 is a parabola that opens upward. So it crosses the x-axis at x is equal to -2 and x is equal to 3. And the graph is below the x-axis on the interval -2 to 3. So that confirms our answer that we previously got. So now another application is finding the domain of an expression. So for example, we are told to find the domain of the square root of 64 minus 4x squared. So the domain of an expression is a set of all x values for which the expression is defined. For a square root, the radicand must be non-negative. So the expression, the square root of 64 minus 4x squared, is defined only when 64 minus 4x squared is non-negative. So then we can solve the inequality. 64 minus 4x squared is greater than or equal to 0. So first we can factor out a 4. So we can divide by 4 on both the left and right hand side. So 64 divided by 4 is 16, and 4 divided by 4 is 1. So we'll have 16 minus x squared is greater than or equal to 0. Now we see 16 minus x squared is a difference of squares. So that can be factored into 4 minus x times 4 plus x and greater than or equal to 0. So we set each of those portions equal to 0. 4 minus x is equal to 0 implies x is equal to positive 4. And 4 plus x is equal to 0 implies x is equal to negative 4. So now rearranging our zeros from least to greatest, we'll have x is equal to negative 4 and x is equal to positive 4. So then we can construct our test intervals. So the first one will be from negative infinity to negative 4, then from negative 4 to positive 4, then to positive 4 to positive infinity. Now for each of those intervals, we can choose a test value. So for negative infinity to negative 4, we chose the value -5. So f of -5 will give us -9. So our inequality does not hold on that interval because we are looking for values such that 64 minus x squared, 4x squared, is greater than or equal to 0. So for the interval -4, 4, we chose the value 0. So f of 0 will give us 16, and since it is positive, then that interval will hold. That means that the values within that interval will all be greater than or equal to 0. So now for the last interval, 4, infinity, we chose the value 5, so f of 5 will give us -9, and therefore that interval is not part of our solution set. So the inequality is satisfied on the closed interval -4 to 4. So therefore the domain of the square root of 64 minus 4x squared is from -4 to 4 inclusive. And now since we had greater than or equal to, that means we can include the endpoints. So now we have our graphical solution. So the graph of the equation y is equal to the square root of 64 minus 4x squared is to the right. So the graph is the upper semicircle of a circle with the center 0, 0 and a radius of 4. The x values extend from -4 to 4, including the endpoints. Here's the profit from a product example, but with more of the steps expanded. So here are some unusual solution sets. So we have the inequality x squared plus 2x plus 4 greater than 0. So the solution set is all real numbers, so the interval -infinity to positive infinity, because a quadratic is positive for every real x. So now for the inequality x squared plus 2x plus 1 less than or equal to 0, the solution set is -1, because the only value that satisfies this inequality is x is equal to -1. Now for the inequality x squared plus 3x plus 5 is less than 0, there's no real solution, so the solution set is empty, the empty set. Now for the inequality x squared minus 4x plus 4 is greater than 0, the solution set is -infinity to 2, union 2 to positive infinity, meaning all real numbers except x is equal to 2. So not every polynomial inequality gives one simple interval. The solution set can be all real numbers, a single point, the empty set, or all real numbers except one value.